So this is going to be a view from the United States. There are numerous things that I want to talk about, and I hope that this half an hour or so, I should be able to finish in 25 minutes so that we will have some time for Q&A. And if not, then definitely we will have time in the panel session afterward. So long, table of contents, I will not go through that because, we will be going through all of this in general anyway. But one thing that I would like to point out is that the workforce development challenge that was faced earlier was the first time was in the 60s. Okay, there were no nuclear engineers, and the 60s and the 70s were the biggest the first renaissance of the nuclear age. We built the most number of nuclear power plants at the time when there was no previous pipeline. So it can be done. It just needs to be properly handled, and with appropriate appropriations to the existing reactors and the advanced reactors. With that comment, let me just point out that this is a really hot topic right now everywhere. Just last week, I attended a meeting of the Nuclear Energy Institute in the United States, actually, and they had commissioned a report that came out October 2023, last month, and the title of the report is Nuclear Energy Industry Workforce Strategic Plan. This was commissioned to a group, and they worked on developing the guidelines for how to develop this strategy for existing reactors as well as for advanced reactors. So there are guidelines in there. I borrowed some of the slides from them, and these are some of the slides that you can see. They have the NEI report on top. No reason to go through this all. I think you should be able to find this report. But the key takeaways are given. They identified in the context of the United States. There are universities, then there are community colleges, and I'll talk about some of them a little later, and the different kind of trades that we are actually interested in. The pipeline strategies, nothing very dramatic. Okay, the standard thing that almost anybody will think about, we need to start the pipeline from kindergarten, K-12, try to attract more number of middle school and high school students getting interested in nuclear, whether they go to university or they go to trade schools or vocational schools, develop partnerships with programs, federal and state policies that promote careers in workforce development in energy broadly and nuclear energy specifically. There are attempts of this kind that are already going on. The federal government, for example, provides some scholarships money to entice students to come to nuclear programs, and there can be more of those. Same thing for the industry. The industry can also try to do the same thing. And the last point here, drive the development of nuclear engineering and related fields at universities. I'll talk much more about them as we proceed. There are detailed, so this is still the NEI report, pipelines propose industry actions and the company actions, and there are lots of bullets there that again, I will not go through. But you can see that there are the standard things that you expect. The K-12 is expected. The American Nuclear Society is supposed to, make it more visible and more attractive. And the universities, the industry, the federal government, et cetera, they have to work together to make this thing happen. So next generation reactors, a separate complete bullet on that, attracting, training, placing, and supporting the next generation reactors. Workforce requires planning with national and international implications. Retirement of skilled laborers is projected to accelerate, and so there will be competition of this workforce that is coming out through the pipeline to go toward existing reactors as well as to go toward the advanced reactor development activities. The current fleet is extending its life to 80 years, and an advanced reactor fleet is expected to deploy in the next decade. Okay, shifting labor markets, and basically summarizing, the kind of activities that I described. So that was the 4 or 5 slides that I took from the NEI report that came out last month. This is kind of a national level activity at from the very top. The workforce development model in USA, just because there are some variations that take place from country to country, I thought it would be good to point those things out. So high school is 12 years, and then you can go to a trade school or community college or university. University is 4 years plus master's and PhD. There are 2-year community colleges that also provide some trade training. But then there are trade schools where you can get training for electricians, plumbers, and those kind of other vocational trainings. So that's the general model in the United States. So when you are talking about developing the workforce, of course, we need to look at the workforce in all of these cases, all of these categories, because they will be needed. One thing that I do not have on the slides here that I was thinking about earlier was that for the Advanced Reactor Development Program, there will be kind of 3 kinds of workforce that will be needed. A workforce that is needed right now for the development of the advanced reactor design. Okay, so we are in the design stages in many cases, and that activity is needed. Sometimes, you need even PhDs and master's level students, definitely. That skill set is needed you don't need welders right now, okay? But you need those high level, skilled people to develop the design. But once it reaches the point of full design completed and certified, now you have to put it in the ground, then you need a different kind of people. A lot of welders are needed, plumbers, electricians, etc., to put the plant in place. And then once the plant operates, then you need the workforce to operate the plant. So this is just another way of looking at, where is, what kind of expertise will be needed. And they will come from different parts. So even when the plant is operating, you may still need some of those, but hopefully this will be a lot less than what we need at an operating plant today, because that's the whole idea of the advanced reactors, that you will need less maintenance and less workforce to operate them. The state of nuclear engineering education, okay? It has been cyclical, up and down. Every 10 years, we see a number of, the interest increases, then it goes back down. After several years of dropping enrollment, nuclear departments are seeing once again renewed interest. More students are coming into the nuclear program. This is all in the context of the United States. So it is true in general in the United States across all universities. Some universities with dormant nuclear degree programs are reviving those degrees. So either they were merged into mechanical or some other department in the last 5 years. For example, they have separated the department and stood it up as a separate standalone department. Which is this bullet. Nuclear engineering minor is also being considered. So because of the increased interest and the support available from the federal government, there is an increasing trend in the number of students, as well as on the part of the university administrators to help develop these programs. This is for the University of Illinois. This is a typical trend that the numbers of undergraduate students in the program was decreasing until about, 4 or 5 years ago, and then it has started to increase. And we expect that this trend, which is fairly mimicking the national trend, is going to continue. Same thing with graduate students. You can see that the number of graduate students has been increasing over the years, and with increasing amount of research money coming in, increasing amount of research that is needed to be done for the development of the advanced reactors, this number has continued to increase. So there are these 2 slides, this one and the next one. These are all the universities that are part of what is called nuclear engineering departments group. Okay, and there's a group called Nuclear Engineering Department Head Organization, and which is composed of the department heads of all of these nuclear departments or nuclear programs at various universities. So this year, I'm the chair of that group, Nuclear Engineering Department Head Organization Group, and it is a 1-year position, and the next year somebody else will be there. And we, compare notes, and we, see what is going on at other universities. We talk to the federal government. NEDHO, this group actually, helps facilitate the interactions of the workforce development component across the country. It interacts with the American Nuclear Society, it interacts with the Nuclear Energy Institute, as well as the federal government and the NRC. So Coming to the specifics of the nuclear degree program. So I'm not qualified, and I'm not going to talk about the other program that we mentioned, the community colleges or the trade schools or vocational schools. So they need to be done. Maybe in some cases, they are much more important than what I will be talking about in terms of workforce development, but this is what I'm qualified to do. I cannot talk about those other categories. Maybe we can discuss some of them during the panel afterward. So nuclear curriculum usually looks something like this, right? So there's a physics, chemistry, math part, there's a nuclear technical core where you have the modern physics, et cetera, and then you have the nuclear thermal hydraulics, you have the reactor physics courses, et cetera, and then some normally what is considered technical electives. Where do these things fit in the context of developing the workforce for advanced reactors? Okay, so this is what I will be talking about in a little bit, because this core, this nuclear curriculum, has been gradually shifting more and more toward light water reactors over the last 40 years, except maybe with the exception of the last 5 years or so, when things have started to change to reflect the need that is coming for advanced reactor development. Back in the 60s and 70s, it was possible to actually go through many of these courses, like the nuclear thermal hydraulics systems class or the reactor physics class, and get a proportional representation of both the fast spectrum as well as the thermal spectrum. Various types of coolants, okay? 40, 50 years ago. But with the increase in the number of light water reactors, BWRs and PWRs, and the need for workforce to work at those plants, the expectation from the utilities, from the employer, was that the person will be trained in BWR, PWR technology, okay? So the universities have sort of, without thinking much about it, have been gradually moving more and more toward those kind of technology discussion, and they talk about spectrum very quickly. There's a fast reactor, but then let's talk about thermal spectrum reactors, because that's what's much more likely that you are going to work at. Except now, over the last 5 years, we have realized that we need to talk more about fast spectrum reactors as well. We need to talk about something other than water as coolant, maybe something other than water as moderator, like graphite. So those things have started to increase. So let me skip that particular one. Nuclear curriculum, you can see the intro class, radiation protection, radiation matter, and the two more important classes. For example, this is your reactor physics class, okay, as well as nuclear systems engineering and design. This is the full reactor system class. These, as I said, these are the classes that need to start to reflect the demand and the need for advanced workforce development part, workforce development for advanced reactors. Technical electives, you can see here, you have the PRA class becoming increasingly important. You have the safety class. Now that safety class also needs to start to reflect sodium safety, for example. I mean, so far, it is all about LOCA. Okay, majority of it is about loss of coolant accidents in a BWR, in a PWR. But they need to change. The only course that actually fairly adequately represents the general requirement is the fuel cycles class. Okay, the fuel cycles class in most universities do reflect the wide range of reactors, because that's the nature of the class and that's the nature of the course. So, except for courses, this is what I just said, except for courses in fuel cycle, which often already contain a significant fraction of the syllabus on advanced reactors and associated fuel cycles, all other courses usually start out with theory that applies to conventional as well as advanced, but very quickly narrows down to BWRs and PWRs. Okay. I already made that point. There are two different ways that one can address the challenge: introducing entirely new courses aimed at advanced reactor concepts, so we can develop completely new classes, or increasing the coverage of advanced reactor concepts in existing courses. So maybe devote a little bit more time to fast spectrum reactors, fast reactors, maybe devote a little bit more time to molten salt, sodium, graphite, and such in existing courses, which is largely what is going on right now, as I'll point out. So to better understand what I did, taking advantage of my position as NEDHO, I sent out a question to all the nuclear engineering department heads. What is it that you are doing, okay, regarding the development of the workforce for advanced reactors? How are your courses, how are your classes being modified? As you know, there are three things, right? 3 or 4 things that differ, right? The neutron spectrum, fast versus thermal, need to be addressed. Moderator or coolant, that combination, and some material challenges. And there are additional things also, right? The reactor physics changes with the reactor kinetics and the stability, and those issues also become different. But in general, I mean, they can all be summarized basically in this. Only a few programs have introduced complete new courses aimed at advanced reactors. Very few, okay? Some have offered these topics under special topics, including we did. Many have introduced modules in their existing courses on reactor physics, nuclear materials, reactor systems to introduce advanced reactors. Illinois and some other universities have offered special topics. So for example, this is the outline of a fast reactor course that was offered at Illinois, believe it or not, about 10 years ago. It was only offered once as a special topics. A good bunch of students, undergraduate seniors and graduate students took it. And now they sometimes, I hear the comment that was probably the most useful class that I took, because now they are in a capacity where they are able to use this. So we had some guest lectures come down to the university from Argonne National Lab, several guest lecturers who came down and gave lectures on these different topics. These are some examples, okay? The next few slides are going to be these examples of the messages that I got from different nuclear engineering department heads as to what their university is doing. Analysis of nuclear systems for the production of useful power. Emphasis is thermodynamic cycles, reactor types, coupling of reactors and power plant. It covers a breadth of advanced reactor concepts in a comparative way across various dimensions, often with many guest lectures from the companies developing these technologies. This was one of the university nuclear engineering department head that sent this to me. Nuclear chemical engineering, we have just hired a new faculty member who does chemical. He does molten salt chemistry. And so that is, now he's going to develop a new course in that area, and that is increasing the trend. Because some of these students have been doing their PhDs in the last 5-7 years, and their PhDs have been on one of these advanced reactor concepts, okay? So if they were working with molten salt, then that's what they are going to bring as a faculty after completing their PhD. Same thing with molten salt, same thing with other types of reactors. So this is going to start increasing. In this course, topics will be presented using case studies relevant to nuclear technology, with a focus on systems employing high temperature, non-aqueous liquids. Let me skip this one, but this is also, you can see the buzzwords, trisulfide reactor. This is West Point, so Army is interested in the pellet reactor, and so they need to start developing the workforce for that reactor, and they have also started to introduce concepts that are relevant to that in the courses. ENU 6937 at the university, modern concepts for nuclear fission reactor systems, including liquid metal reactors, SFR, et cetera, about 6 weeks, gas-cooled reactors, about 5 weeks, and advanced reactors, Gen 3, Gen 4, Gen 3, 3+, et cetera, approximately 4 weeks. And the other course, ENU 6143, for liquid metal and gas-cooled reactors include thermal modeling, reactor safety, licensing, reactor physics, but in the context of liquid metal. Once again, you can see another example of a course at the university, fast reactor physics and computational science. And this leads into 3 lectures on HTGR, TH analysis, 2 lectures on FHR, MSR, molten salt, introduction and salt heat transfer, and 1 intro to digital twins in nuclear application. Digital twins is becoming big thing in the nuclear development in the industry, and that is also being introduced, but in a somewhat ad hoc fashion. Okay, some universities are doing it. One university starts a program, they put in a 1 week long treatment in their reactor simulators for advanced reactor concept. This is another way of introducing the advanced reactors, okay? So before the advanced reactors come in, one can actually develop an advanced reactor simulator, okay? And some of these, the companies that are actually developing advanced reactors, they are already contracting with simulator developers to develop reactor simulators, and some of these are going on university campuses, and they can be used to actually help students learn the ins and outs of advanced reactors using reactor simulators. And that brings me to the last part of my talk, advanced research reactors for education and training. Now, it is, for the last 60 years, the research and training reactor is an integral part of university education at American universities. There are still about 30 or so, close to 30 research and training reactors on university campuses. They are part of the curriculum. There are reactor labs that are required in the curriculum. Students go, they conduct experiments, they learn how to operate the reactor. They can even they operate the reactor and get an RC license to operate a reactor of that kind, okay? So this has been an integral part. These are all light water reactors, good number of them, like trigger type reactors. But now, if we are going to be talking about advanced reactors with different spectrum, salt, fast reactors, molten salt, sodium, metal, gas-cooled reactors, high-temperature reactors, where is the experience going to come from for our student body that is coming out? And the challenge is going to be that in the light water reactor systems, there was one type, right? All the reactors, BWR, PWRs are all light water. Now we are talking about different coolants, at least 3 different kinds of, 3 different bins of coolants, and then different ways of moderating reactors or not moderating the neutrons. So there is a movement starting to see if there is a possibility of bringing a new advanced research and training reactor to university campus, and maybe more than one. So University of Illinois actually initiated some years ago. We then finally we partnered with USNC, and we are exploring the option of getting a high temperature gas cooled reactor, a small one, a micro reactor, about 10 megawatt, to our university campus that can be used for research, for training, as well as to produce power. Okay, the power will be available. Maybe it can be used to, it can go, this is actually a coal plant on campus, and maybe it can replace coal, and it can be used to produce electricity. And when electricity is not needed, maybe it can be used to produce steam or hydrogen for the fleet of buses that are on campus that are running on hydrogen. There are already 2 buses, and they're planning to get some more hydrogen-run buses. And there's also steam need on campus. So there's a possibility of all of that. So this was the cover of the Nuclear News magazine in April of 2022 issue. And this is the old trigger reactor that used to be on our campus, which is no longer there. But this has been decommissioned. But the idea is to bring in a new one. It can be used for hydrogen. We are partner in one of the big 7, the 7 hydrogen hubs that have just recently been announced. University of Illinois is partner with Constellation and other regional companies. And the idea is to also explore the possibility of advanced reactor and the training, the workforce development component, where the reactor is then possibly expected to not only produce electricity, but also process heat and other applications of thermal energy that will come out. And very recently, North Carolina State University, they announced that the state of North Carolina has given some amount of money, $3 million, to explore the possibility of a research and training reactor on their campus. A couple of other universities have also announced similar intention to explore the possibilities. So this will be very important for the purpose of workforce development for advanced reactors. Maybe the last couple of slides, that other new courses on enabling technologies. Now, these are not necessarily being offered by the nuclear departments, but increasingly made available by other units on the college, in the College of Engineering, and the workforce development for the next generation reactors, workforce with the nuclear background. We think that they need to be aware of these enabling technologies, because these enabling technologies will make it possible to actually develop a better advanced reactors. And as we all know, many of these, like 3D printing, additive manufacturing, AI and machine learning, robotics, data analytics, HPC. Our department acronym is NPRE, Nuclear, Plasma, and Radiological Engineering. So NPRE is developing a new degree called, which will be a hybrid between nuclear and data science. So it will be a joint degree, okay? And this will help our workforce that will come out of one particular kind. I mean, they might be a little on the light side of the nuclear, but then they will be good with data science as well. We also have MEng in Energy Systems degree, which is a master's degree, Master of Engineering in Energy Systems in general. That energy systems can be wind, solar, geothermal, grid, etc., all kinds of energy-related things. But then there's, of course, nuclear is also a part of that, and that Master of Engineering can be used actually quite nicely to help develop the workforce in a much shorter period of time, because this is a one-year degree. So you bring in a mechanical engineer, and they go through this program, and they focus on nuclear power, and in 1 year, maybe 3 semesters, they will be ready to be employed by some nuclear company. This is basically what happened in the 60s and 70s. Okay, when there were no nuclear degree programs, it was the undergraduate people with chemical engineering and mechanical engineering and physics and electrical engineering degrees. They came into nuclear, got their master's degree or PhD degrees in nuclear, and then helped build the first or the second generation of nuclear reactors, Gen 2 reactors, in the 60s and 70s. So in the United States, I mean, that number went from about 5, 10, 15 to about 100 in a matter of about 2 decades, 2.5 decades. And this is, I mean, the workforce need at that time was, we were able to handle with a much smaller number of nuclear engineering departments. Now we have quite a bit. So anyway, I'll stop there. Thank you very much.
ありがとうございました。Thank you very much, Mr. Wedding. それでは、会場からご質問があればお受けしたいと思いますが、いかがでしょうか。どうぞご遠慮なく挙手でお知らせください。いかがでしょう。皆様ご質問ございませんでしょうか。ではですね、オンラインから、1点ご質問をいただいておりますので、ちょっと日本語で私の方から読ませていただきます。米国において原子力の人気、不人気はこれまで周期的に変わってきたということですが、その要因は何でしょうかというご質問をいただいております。ただいま通訳でお伝えいただきますのでお待ちください。
So the question was, why is the nuclear interest in nuclear so cyclical? So 60s was big time, very popular. Nuclear was very popular, and even in the 70s. But then, every time an accident happens, so the 3 Mile Island, basically in 1979, that started to drop a little bit, and then Chernobyl, the half-life of those effects. After Chernobyl, it took many years, maybe a decade or so, and then it had started to come back up near the end of the century. but then, it was gradually increasing, but then Fukushima happened. Okay, and then that was another big hit. So basically, these accidents have been the reason for the cyclical interest in nuclear. It takes some time for the previous generation to get out. The new kids who come in, they are much more enthusiastic about nuclear. They want to start coming back because in their memory, they don't remember, they didn't experience 3 Mile Island or Chernobyl or maybe even Fukushima now.
ありがとうございます。会場からのご質問はございませんでしょうか。ありがとうございます。それでは以上をもちまして本講演終了させていただきます。ご講演いただきました、リズワン・ウディン様に大きな拍手をお送りください。ありがとうございました。